Now that we have already discussed uniformly accelerated motion, let's move on to talk about projectile motion. So projectile motion is sort of like a continuation from uniformly accelerated motion, because one of the components of this projectile motion here will also be moving with uniformly accelerated motion. But let's study it deeper. So projectile motion is a motion that is determined entirely by the effects of gravitational acceleration. So if you throw something into the air, or you launch something, or you drop something, or you propel, or you push something off the cliff, when those objects are in the air, you are not touching any surfaces, right? The object is not touching any surfaces. So the only force acting on the object will be the gravity. Okay, there's gravity, but there's no ropes pulling, so there's no tension. There's no wall, so there's no normal force, and there's no rough surface, no friction, and you have no external force pushing it. So once an object is in the air, if it has no, what do you call it, Doraemon fan, no helicopter propeller, no thruster, no booster, just an object, then the only force experienced by the object will only be the gravity. So when those objects are in the air, the motion that that the object travels, we call it a projectile motion, because this motion here is determined entirely by the effects of gravitational acceleration. Okay, so a projectile motion usually traces a path that is that looks like this, so what we call it a parabolic path. So projectile motion, it traces out this kind of path, and we call this kind of path as projectile. That's why we call it projectile motion. The path here, we call it as projectile. So I've labeled here using blue dots the position of the object at various moments. So you can see initially, for each second that has passed, it travels through a greater distance, but slowly when it reaches the peak, it travels less distance. Then when it falls back down, again it speeds up, so it travels more and more distance with time. Okay, so this is sort of like a general way of visualizing a projectile motion. And here I also labeled the purple arrows on each blue dot, because these purple arrows here are representing the velocity vector at different moments. So the velocity, we know that instantaneous velocity will be in the direction of motion. So these purple arrows here are in the direction of motion. As we can see, it follows the line of the parabolic path. Okay, so why do I show this graph here? Why do I show this projectile motion here is because I'm going to resolve this projectile motion into two components. Okay, projectile motion, it's motion in two dimensions. So it's slightly different from all the motion that we have studied in chapter 2, because projectile motion, you consist of motion in the x direction and the y direction. It's not only one direction, it's two direction involved, two dimension involved. So when we are solving motion involving projectile motion, it's important that we are able to resolve it into the two components, which are the x components and the y components. So let's look at how we do that. So we can break this velocity vector, this purple vector here, into its x component, the blue arrows, and its y components, the red arrows. So at different moments in time, you have different x and y components of velocity. So let's try to investigate how the x components of velocity and the y components of velocity, how does it change with time. So I'm going to pull all the y components to the y-axis, and I'm going to pull all the x component to the x-axis. Something like this. I create my y-axis, then I pull all of the motion onto the y-axis. Okay, because I'm going to study the y components and the x components separately. Okay, so this is the motion in the y-axis. If you just focus on the y-axis, you see that the object slows down when it's going up. Why do we say it slows down? Because before that it travels a great distance, then after that it travels less distance per unit time has passed. So you can think of it as the first second it travels this much distance, second it travels by this much. So the distance traveled actually decreases with time until you reach the peak. Then when it falls down, the distance traveled increases per unit time. so it speeds up as it goes down. So this is what's happening on the y component when you are looking at the projectile motion. This is the y component. How about x component? So we bring down x component again. So these are the x components, and if you bring it down, I believe you can sort of see a pattern which is quite different compared to the y components. Okay, as you can see here, all of the arrows here have similar length. In fact, they have identical length, means by the velocity, the x component of velocity at each moment of time at all throughout this journey over here, the x component of velocity remain the same. It's always the same magnitude of velocity in the x component, but for the y component, it changes with time. Okay, so let's investigate the x component first. We call the x component the horizontal component or the x component. And as we can see, it's motion with constant velocity. Because the direction of the velocity is always the same, it's always pointing in the same direction. And the magnitude, which is the length of the velocity vector arrow, it's always the same throughout the whole journey. So we say it's constant magnitude, constant direction of velocity, therefore constant velocity. So when we say constant velocity, we know that the initial velocity in the x direction will be the same as the final velocity in the x direction. In the x direction, the velocity never change. In the x direction, the x component of velocity never change. So you should expect the initial velocity in the x direction should be the same as the final velocity in the x direction. And because they are the same, we also know that no change in velocity means zero acceleration. So you should expect in the x direction, your acceleration will be 0 meter per second square. So this is what's happening in the horizontal component. Let's look at before I move on to the vertical components. So if you write down your SUVAT for the x component, remember to put in all your subscript x here. And what we know because of this analysis here, we know that the x component acceleration is always 0 meter per second square. So this is fixed if you are talking about projectile motion. And we are neglecting air resistance here, so we don't need to consider wind slowing down us or what. Okay, so let's move on to the vertical component. Vertical component, it's this component over here. So just now we mentioned that for the first portion of the journey, we can see that the object is slowing down. The distance traveled per unit time decreases. But for the journey going downwards, you can see that it's speeding up because the distance traveled per unit time actually increases. So if it slows down when it moves upwards and it speeds up when it moves downwards, what kind of conclusion can we make about the acceleration? We know that the acceleration must be non-zero because the velocity changes. If the velocity changes, it means the acceleration is non-zero. So, but what we want to find is whether it's pointing upwards or pointing downwards. Then you have to recall, to determine these kind of things, we have to remember that if an object is speeding up, the velocity and the acceleration are in the same direction. If the object is slowing down, the velocity and the acceleration are in the opposite direction. So we see that the first portion of the journey is slowing down. So means by if our velocity is pointing up, our acceleration must be pointing down. So we can know from the first portion of the journey that the acceleration is pointing down. How about the second portion of the journey? The second portion of the journey is speeding up. So the velocity and the acceleration must be pointing in the same direction. So if the velocity is pointing downwards, that means the acceleration should also be pointing downwards. So we know from the first portion of the journey and the second portion of the journey that the acceleration is always pointing downwards. And this is what we know for now. The acceleration is pointing downwards. And because we always follow the Cartesian coordinates where pointing upwards is positive, pointing downwards is negative, therefore we know that our y component of acceleration must be a negative value. And after that, if you move on to chapter 4 later, when you study about forces, you know that because we know that projectile motion is affected only by gravity, you happen to know that this acceleration here is due to gravity. And because it's due to gravity and you're on Earth, it has a specific value for its acceleration. So we call the y component of acceleration to be equals to negative g, where g is acceleration due to gravity. Negative means it's pointing downwards. So the magnitude is g, that's acceleration due to gravity, negative is downwards. And if you put into numbers, that's negative 9.81 meter per second square. So G here is the magnitude of the acceleration due to gravity, therefore there's no sign. G is equal to 9.81, but if you attach a negative in front, it becomes negative 9.81. So the y component of acceleration is negative 9.81, not positive 9.81. G is 9.81, not negative 9.81. So everyone have to be clear about this. So once we know that when we build our SUVAT later, our y component of acceleration will be negative 9.81 meter per second square. And the rest we have to look at the situation to determine it. So what are the keys for our discussion until now? The keys that we need to know is, for any projectile motion, the acceleration in the y components should be negative 9.81. This is fixed as long as you are on Earth. Then x component of acceleration must be 0. So this is the characteristics of a projectile motion, and it's summarized in this portion of the table over here. So how are we going to solve questions involving projectile motion? Well, we know that since we are building this table here, we can continue with the steps involving uniformly accelerated motion. So we still do the same thing. We determine our initial and final position, build all this table, we determine the appropriate equation, then we apply the equation, substitute and get answer. So we'll be using these equations that we've been dealing with in the previous section on uniformly accelerated motion. So we'll go through a few examples later to see how we apply these equations to solve projectile motions problems.